In this lesson, we're going to be talking about basics of functions and their graphs. The first objective is find the domain and the range of a relationship. Now, a relationship is going to be for every x, there is a y value that corresponds to it. Not all relationships are functions. However, the domain of the relationship is going to be the value of the x. So domain is the same as what possible are the possible x values. And I see that in this relationship the possible x values are 0, 1, 4, and 8. So this is the domain of this relationship. The next question is, what is the range? In a range, that is, what are the resulting y values? In this relationship, the resulting y values are -5, -2, 2, and 9. So this is the range of the relationship. Objective 2. Determine whether a relationship is a function. A function is a correspondence from a first set called domain to a second set called range, such that each element in the domain corresponds to exactly one element in a range. A function can have two different first components with the same second component. However, the opposite is not possible. What does this mean? Every time, for every single x not 1, the result is always going to be y sub 1. It is not ever going to be two different values. If this happens, that's not a function. It is possible two different x values to reflect in a single y value. That's possible. And that's a function. So let's check, for example, 2 and 3, which of them is eventually a function and which is not. Well, I notice that in example 2, the domain consists of zero, 1, 3, and 5. However, the range consisting of 3, 2, 4, 6, and 9, 6 and 9 are produced based on the same domain value of 5. This is not possible, so that's not a function. Let's look at example 3. In example 3, the domain consists from 3, 5, and 6. However, 3 produces two y values. 3 produces the value of -2 and a 0. And 5 produces 1 and 6 produces 2. 3 produces two values. Since that's the case, this is not a function. It would have been a function if the example was made of 3, -2, 5, 1, let's say 6, 2, and let's say -3, -2. Since all x values are different, even though the y value for two different x values turns out to be the same, this is going to be a function. Objective 3. Using function notation to evaluate a function. Now, using f of x is the same thing as saying the y value. It's just more convenient way of showing the y value because y depends on how much the x value is. So we read this notation f of x or f at x. We never say f times x. It doesn't mean that. It means what is the y value, the f or the y value for this specific x. So for example 4, I need to evaluate each function at the given values of the independent variable. We call x independent variable independent because we choose what x to be based on circumstances or based on the question given. But the y value or f of x changes its value based on that independent value. So we call f of x or the y value, we call it dependent value variable. Now, what is the domain? Notice that in this question, which is linear function, f of x is 2x minus 3. There is no any problem plugging any values. We can plug in f of 0, for example, because 2 times 0 minus 3 is equal to -3, or we can plug in f of negative numbers, let's say -10, 2 times -10 minus 3 is going to be -23. I didn't have any trouble calculating the problem. I can plug in positive values, negative values, zero value, every value. When that's the case, we say the domain is all real numbers. And all real numbers in interval notation is going to be from -infinity to +infinity. Well, to calculate f of -1 means in this machine, f of box, I'm going to be thinking of 2 times this box minus 3. Let's say that's what I'm thinking. So when I plug in a -1 in this box, then on the place of x, I'm going to replace with -1. So that's going to be f of -1. I'm going to copy it down underneath. F of -1 is going to be when I replace x with -1. Everything else stays the same. And the result is going to be 5. What this means, that's one point from this line, this linear equation, and this point is the point -1,5. So every time when x is equal to -1, the y value is going to be, and that's -5. I missed my sign. Oops. -5. Now f of -x. Well, exactly the same way in my box here. Instead of -1, I'm gonna put -x and see what this machine is gonna produce. Well, f of negative x is going to be 2 times negative x minus 3. Well, negative x times 2 is negative 2x minus 3. And we cannot continue simplifying this expression. It's as simple as it is. So when we plug negative x, we ended up having a y value of negative 2x minus 3. And that's my final answer here. And I'm gonna square my other answer above. F of x plus 3. Similarly, every time when I see x in the problem, instead of x, I'm going to say x plus 3. So f of x plus 3 is going to be twice x plus 3 minus 3. We can use distributive property to simplify here. This is 2x plus 6 minus 3, or finally 2x plus 3. And this is the resulting value. That's how much y is when x is equal to x plus 3. The next, f of negative 2. I need to plug in negative 2 in my box. And that would produce f of negative 2 is equal to 2 times negative 2 minus 3. F of negative 2 is equal to 2 times negative 2 minus 3. The result is negative 4 minus 3, or negative 7. Example 5 is similar, it's just containing quadratic equation, but again, as in the previous case, I'm going to be thinking f of some box is equal to whatever I have in this box to be squared, and then minus 4 times whatever I have in that box, minus 5. So that's the machine, that's how it looks like, this function. Notice that again in this example, whatever value I decide to plug in for x, I would always have a solution, because every number can be squared, every number can be subtracted or added or multiplied by 4 or taken 5 off of. So the domain again is going to be from negative infinity to positive infinity. Notice that in the interval notation from negative infinity to positive infinity, we never put square brackets. We never say square bracket infinity, because square bracket stays for value included. Infinity is infinite, so it cannot be ever included. So that's not appropriate notation. All right, so we're going f of negative x. So again, we're going to put negative x in our box and see what is the result. F of negative x is going to be negative x to be squared. Notice that I'm putting parentheses around negative x because the negative sign is also squared, minus 4 times negative x minus 5. Negative x squared means negative x times negative x, and since two minuses result in a positive value, the result here is going to be positive x squared. Negative 4 times negative x is positive 4x minus 5, and this is my final answer for the first requirement. The second requirement wants me to put a minus sign before the f function. So the x value doesn't change. These two expressions are identical. What is changing is a minus sign in front of that function. So this minus sign is going to be in front of this whole expression. So negative f of x is going to be put a negative sign up front of the entire expression from the right. Distribute the negative sign, negative x squared plus 4x plus 5. The next example, f of negative 2. I'm going to play with my boxes again. In the boxes, we need to put a negative 2. So we end up having negative 2 to be squared, minus 4 to be multiplied to negative 2, and finally subtract the 5. The result, negative 2 squared is a positive 4, negative 4 times negative 2 is a positive 8, minus 5. Altogether this is 12, minus 5, 7. F of x minus 1, so I don't jump up and down, I'm gonna copy again here my machine. And substituting it, put it here. So that's gonna be x minus 1 squared. I'm putting x minus 1 in the box. So x minus 1 squared minus 4 times x minus 1 minus 5. Notice that x minus 1 squared is the same as x minus 1 to be multiplied by itself. And here we can eventually factor the minus 4x plus 4 minus 5 and simplify. We need to do distributional property here. I'll remove this box, it's not needed anymore. Or should I just leave it here? So f of x minus 1 turns out to be x times x is x squared, x times negative 1 is negative x, negative 1 times x is negative x, negative 1 times negative 1 is positive 1, minus 4x plus 4 minus 5, and finally combine the like terms. Like terms are negative x and negative 4x, that makes negative 6x, and 1 and 4 makes a 5, and 5 minus 5 is 0, so that's how far we can go. I'm gonna square my answer. For objective 4, we're going to be recognizing functions through something called vertical line test. So provided that each x value is supposed to have only one y value, for each x value, I'm supposed to be having only y value. Notice that if I select some of these points specifically, I don't see which one that point is, it doesn't matter. Let's say negative 2. If I select this particular value, notice that for this particular value, I end up having 2 points. If I say that's a negative 2 and that's a negative 2 and that's a positive 2, then I'm getting 2 different points provoked by negative 2. This means that's not a function. Function would have, for every negative 2, would have always the same y value. To be a function. So that's not the case. Well, how I catch this from a picture, from a graph, it's extremely easy. We apply the vertical line test. We pass a vertical line through the picture. And if we see that the vertical line crosses at least at one place twice the graph versus 1, we know that this is not a function. So, clean that a little bit. So that's going to be not a function. Or versus the second case, wherever I put my vertical lines, I see that they always cross the graph at exactly one place, which means this is a function. Let's look at question here, C and D, very similar. According to the vertical line test, example C would be a function again. It doesn't matter that if I have a vertical line here, I don't meet the graph. That's absolutely fine. What is not fine is to meet the graph at more than one place. And again, for example D, vertical line is going to show me that this is also a function. And with this, I'm going to conclude this video.